quiet, quiet Friday afternoon. Most people taking a break after Halloween or focusing. I saw some people like doing focusing. I saw some people like getting ready for midterms or something, like round 5 of midterms. I don't know what's going. I don't know which classes are. Cool. And main thing for today was just last time I was kind of giving a tour and like speed running through Pendulum project for this module 3 project. Today, trying to wrap that up, like if there's any missing pieces or if you still had questions about anything, we can jump into that. So project 3. So how's it going overall? Anything like interesting? Did you notice anything like as you were doing it that was like, oh, I didn't expect that, or oh, that makes sense. I never thought of this before. What was going on? It's just us, a small group. You can speak freely. There's only so many people to judge. Let me check in and see what people are up to, and then come back up and kind of share what we've been seeing overall. Yeah. Okay. Yep. Yeah. Yeah. Yeah, because if it's like constant velocity, then you have like constant slow. Sorry, constant acceleration is constant slow velocity for all the time. It's constant straight line. Yeah. Oh, sorry. I think it's just in that case because this yeah. No. Okay. Yep. Yeah, for the most part, like if you run from top to bottom, you'll get something. Stuff just sort of works. At least it's supposed to. Yeah, exactly. Oh, like where those equations of motion came from? That one. I guess I can do it up on here. So, as a review of like what is the equation of motion of a pendulum and how do we get there? Usually, with this class, we've always been using sum of the forces equals mass times acceleration. So with this pendulum, it's like moving left and right and up and down. But there's one constraint on its motion, that it's got to move along some kind of circle, like L has to be constant that way. So we can use cylindrical coordinates to describe, like, all right, L is constant, that's my radius, and then R dot is going to be 0. So R equals L, R dot equals 0, R double dot is 0. And when I look at what forces there are, there's some kind of tension keeping that pendulum on that curve. And then we have gravity is our main like driving force, just the constant force of gravity. And then overall, if I'm going to use those cylindrical coordinates, I have some kind of MA theta and some MAR. And those accelerations, I can always look them up. They're always the same definitions. A theta is R theta double dot plus 2 R dot theta dot. So in our case, this one's going to be 0. AR is always R double dot minus R theta dot squared. And that one's going to be 0 as well. So when I look at those two equations, first equation is something to tell me about like tension along that R. So negative T plus mg cosine theta is a negative m r theta dot squared. That one's not really an equation of motion. It's just telling me like if I'm moving and if I'm in a given location, that's how much tension is required to keep the pendulum from swinging away. And then the second one is that negative mg sine theta is mr theta double dot. And that's my main like equation of motion, that theta double dot is a negative g over r, where r is L, times that sine theta. And I know it's an equation of motion because it's relating like the variable that I'm trying to describe. It's a second derivative related to a first derivative. Sometimes it's second, first, and 0 derivatives, like acceleration, position, and velocity. And then sometimes also time, but in this case, we just have like a natural equation that acceleration, the bigger the angle, the more acceleration I have back to 0. That's where that, so that's like the start, the preliminary to get to the start of that project 3. Is that what you were asking about? Yeah, there, what we're doing is taking initial values. If I know initial angle and initial velocity, solve for what theta is for the rest of the time. Theta dot is. Yeah, exactly. Because the only thing that I included was constraint force of tension and gravity. So there's no drag, no friction, and it's enough to tell us a lot about the problem. But if we wanted to say something's slowing it down, we have to add drag. Drag would make the most sense. Friction with a it's not zero. Oh, if you want to model what the string is doing, that vibrating, or are you thinking yeah, this is just assuming that most of the weight is at the tension. And that's a pretty good approximation. That's 10 times heavier than the first one. Otherwise, you could think of it as like a compound, like a rigid body with distributed mass. Oh, the cylindrical coordinate? No, yeah, nobody's used to it. But it does make it easier to like get one rather than having like acceleration x and acceleration y and solving simultaneously to both dependent on each other. Yeah, that part is okay. There wasn't really a lot to write about. So like when you say the biggest difference is linear numerical, what are you saying? Between linear and numerical. So like what's a large value? Large value. So you like what over a certain value, that. Yeah, and then what is the difference that you're like when you say it's different? What's different? What are you pointing at? Oh, all right. Okay, so if it's the periods, then when does it become different? Like when you see a noticeable difference in time period, how big is something like this long? What's your threshold for big difference versus small difference? So could I just set should I say noticeable difference then? Because we're talking about biggest, right? It asks for biggest difference, right? So for what you can get and say that the bigger difference is decimal point. Okay. Yeah. It's kind of what I was writing. But so do you want to know when there's noticeable difference? It's up to you, like how you want to say that. So like you were saying that there is a difference, so I'm asking what made you say there is a difference. Yeah. Like, but when you look at the graph, because the lines are always different. Yeah. Oh, yeah. Between the time periods. Okay, so time period is what you were thinking? That's what I would, yeah. Okay. Oh, I guess, and amplitude. Yeah. Okay. Yeah, time period. The time period and at least for amplitude of the acceleration. Yeah. Yeah, like that would make sense. Separate to see the game. See it kind of here. It's hard to see. Yeah, for velocity and position, I think for the most part. I mean, there's a little bit of, I guess for velocity, that you're going to see it. Tension. Yeah, tension. Well, the tension is based on velocity. Yeah, and part of it is like practicing. You know what you're looking at, and you have like a sense of the physical. I understand that, but you need to explain why. What are you looking at, and what are the numbers that you're getting out of that graph? Yeah. All right, cool. So another good question that we're kind of looking at is like, or wait, let me see, what angle am I at? Right now I'm at pi over 2, so we'll leave it there. So if what we were looking at before was the question of like, okay, well, I notice the biggest difference when the angle gets bigger. And if I'm trying to describe that, like I'm making, so this is like a technical report. It doesn't have to be like a long 10-page paper, but it is a technical report where I have all these graphs and I want to explain what are the important pieces of these graphs. So here I'm at an initial angle of pi over 2. So I have 90-degree start angle. The amplitude of my like pendulum oscillating for position is exactly the same. So that's not a difference that I'm noticing between linear versus nonlinear. Meanwhile, let me copy this over. Meanwhile, this time period T nonlinear versus T linear, those are significant differences. Now I'm looking at something that's like 2.75 versus 3.1. So error is 3.1 minus 2.75. So like a quarter of a second difference. So if I'm trying to write a response of like, where did I see the biggest difference? And I want to talk about how the angle, the size of the initial angle is changing the difference. So for larger initial, if I could spell, theta values, the time period increases. For example, at theta 0 equals pi over 2, time period error is 0. What did I say? 0.26. Like this is how I would try to explain like, hey, these are the important things that I'm seeing here. And then we were also looking at the fact that, hey, this amplitude and these amplitudes are the same, but these two are definitely not. Because this amplitude is pi over 2 times g over L. But this one is g over L. So the bigger that initial angle, the bigger the change in that acceleration amplitude for that wave. Do you know how I got pi over 2 and g over L for amplitudes? Magic. I'm just very good at reading graphs. No, right? Nobody's that good. Theta double dot equals negative g over L times theta. Theta is going 90 to 90, 90 to negative 90. So max theta double dot equals g over L times pi over 2. Whatever the biggest angle is, that's my biggest acceleration. And this is that linear one. And nonlinear, theta double dot negative g over L times that sine of theta, max theta double dot. What's the maximum value sine of theta can be? 1. So the max that I can possibly get is negative g over L. And if I have a smaller angle, so if sine of, if I'm trying to say sine of theta, like maybe theta only goes to 45 in yours, and the max would be sine of 45. That would be like your max acceleration. And then if I really want to tell, like, show people, we'll get this back down to like 10 degrees, pi over 8, did I say 18? Or 18 degrees. So 18 degrees. Now my curves are kind of lying right on top of each other. So this is different for small angles, e.g. theta 0 equals 18 degree when time period error is less than, I can't really see a difference in time period, so it's got to be less than like 0.1 or 0.01, like somewhere around there, at least from visually. There's ways that we could calculate it, but if we're looking at a graph, kind of trying to make a guess, we can't see the difference, so it's less than 0.1 seconds from the graph. I guess from reading the graph. Yeah. And I think last time at the end of class, I was showing like tension for linear and nonlinear, so we could take if you solve for t in this first equation, you could plot that and compare what is the linear tension versus nonlinear tension, and see what the difference is. That's like one other way that you can compare these plots. And again, for small angles, no difference. Like 15 goes from 15.5 up to almost 18 and back. And that depends on how heavy you consider the pendulum. Like we could make it a big honker, make it 10 times heavier. 5 kilogram, 10 pound swinging thing.
So if there's a slight but no, there's like a very small error that you can see, it's still probably less than 0.1 on the graph.
Yeah,
so
we could.
I don't know what you were using for your.
Like how I calculated.
No, I don't know what you were using for your pi value.
Oh, this was pi over 10 for theta, and then like instead of pi over 10, if we do.
I was looking at like pi over 8. You can see something, but barely.
Oh, pi over 8.
Yeah.
Yeah, like pi over 6 is another one.
Oh, pi over 6 is noticeable.
That one you can kind of see, like a little bit.
So like that one, I would say you're definitely at least 0.1 second off.
That one's probably about 0.1 because we can see it. Like we can definitely see that there's difference. What's my guess? Just from trying to read. cosine waves floating along. How's it going? Progress? Okay. Were you trying to work through this project? Oh, okay. Oh, okay. All right. Cool. That's good. Yeah, the main part is kind of like you can play around with like what the lenses are. You can change gravity if you want, and then see like where there if like when this. And part of it's like giving you like, when is it worth doing a full like non-linear numerical solution? Okay. Okay, that's fine. Do you have like questions on it or? Yeah. No. Yeah, and that one, I feel like all the writing, at least when I was a college student, all the writing training we got was like creative writing, like just describing feelings or something. And then I asked, when someone asked for my first like technical report, what is this garbage? I don't know. So they went. Trying to get chances. We change it to like down. We click code, change the markdown. Now it gets nicely formatted. Okay. Like with tension. Oh, did you want to do something else? Yeah, like if you're plotting tension, one of the main differences is like for every time period you see tension go through 2 cycles, because it has that like theta dot squared term in it. So I don't know, kind of interesting, and it's because there's symmetry. Like the tension when it's positive angles has to be the same when negative angles. So that one's kind of interesting. But we could also say mgh plus 1/2 mv squared is constant. So this is going to be mgl1 minus cosine theta plus 1/2 m L squared theta dot squared. All that is constant. And really I could drop, if I get rid of the m's, it's still same constant divided by m. So I could look at like, am I conserving energy with these 2 approximations? I want this. So I'll say, oh yeah, and I had changed my G, didn't I? G is 32 in mine. Do I want to leave that? I'm going to change it back to 9.81. And I just have a 5-point So now I could say potential energy. I use V for potential energy. You could say PE is going to be G times L times 1 minus cosine of theta. Oh yeah, this is the linear, right? My kinetic energy for linear is going to be 1/2 times L squared times d theta squared. And if I add those two up, it should be a constant. But it is not. And that's a little weird because all we did was take a linear equation and solve it. Like, we should still have conservation of energy should still be a thing. So let's compare that to non-lin. It's going to be the same. So I'm just going to take these two and copy them. Instead of theta, I'll call this sol dot y 0. And this one's going to be sol dot y of 1. And there we get a little bit more of a constant. It's still like not quite constant, but it's closer to a constant value than that first solution that we got for just adding up those linear solutions. It's kind of weird. Yeah. Do you know why that is? Like, why? Because the linear solution, at least the way the answers come out, it's never going to be like strictly energy is constant. It kind of oscillates like this each time. Because really, this term should be like a GL over 2 theta squared instead of like a cosine theta like that. Because we're making a linear approximation, then so if we use that, if instead, I think it'll work. I actually haven't tried it, but I'm pretty sure this would work. G times L over 2 times theta squared. Yeah. Then we get a flat constant line, which is what you would expect, is that potential plus kinetic is always a constant value because there's no drag or anything. And these bumps, the red bumps up and down, that one's just from the fact that we're using a computer to step through in tiny increments. It does introduce some errors, but it's a pretty good approximation. Yeah, that's kind of the key there. This is like the advanced of what else could you do with this? Like, what else could you plot? Because this is like next module's exploration is momentum and energy, looking at conservation energy, impulse momentum methods.
Yeah.
That one is just taking like the like here. This is my nonlinear angle, and this is my nonlinear solution. Theta dot.
Okay.
And that's all. I was just taking the exact same equations of kinetic and potential energies,
right,
but plugging in either a nonlinear or a linear.
Okay. I see.
Yep. Yeah. And they should be constant.
Mm-hmm.
Kind of constant. Pretty close. Oh, nice. You were doing the same thing. Looking at like total energy. Okay.
But I thought the more accurate.
Yeah. Okay.
Right now, the trash one is
Okay. I mean, they both have they both have the same restorative rules, right? They're both using gravity. So it's an approximation of like the force due to gravity because we're linearizing, like we're just taking or extrapolating linear term beyond zero. It's only accurate when it does introduce error that way. Accuracy. That was a good question. So the accuracy, like in that second question, it asks like which solution is more accurate? Is a nonlinear solution always more accurate? Is it better? Should we throw out all of our differential equations and linearizing functions? Is it and always do the nonlinear integration method? Or are there times when the linear solution is more accurate than that numerical kind of nonlinear solution? What did you think? Did anyone have like a strong opinion on which one is more accurate?
I mean, I don't have a strong opinion, but I still think like it's not like more accurate, but like it's easier for a human to use like a linear. I feel like it's very for like smaller angles, like pretty much the same.
Yeah.
Versus like a computer that doesn't have numerical, use the more accurate one.
Okay.
Like the non-linear one, because that's like more accurate.
Yeah. Yeah, so with the numerical solution, and kind of when we were looking at this difference between did I mess something up? It looks different, right? Than what I had before. Anyway. When you look at like the answer that red curve gives us, that's like the nonlinear total energy, and there's definitely like error accruing there. Like it's not, and part of that is just the fact that you're using a computer to do things for you. Like you don't have an equation that you can evaluate at any point in time. We just have like discrete values of like, here's the answer. And so in terms of like, what is the most accurate measure of acceleration for a given angle? Like sine of theta is a much better like way to describe how much that angle will change. So integrating The numerical is more accurate that way. Like it's a better representation of what forces are involved. But when you have a linear solution for small angles, you have an exact function that you can evaluate, and there's no error when you evaluate those terms in your function. So it is a very accurate way to do things as long as your angle is small. And you just have to, and part of this is just figuring out like what's an acceptable level of small angle for you or for your family. I don't know. Depends on what you're doing, who your family is, whether or not you talk about small angle approximations at Thanksgiving dinner. Yeah, usually pi over 6 is about right for me. But pi over 6 for change, those energy changes are a little different. And you can we do it this way? I don't know if it's gonna like me with this. No, it didn't like it. We can look at like kinetic and potential. It's a little too busy with everything on there. Like how they minimum potential is at maximum kinetic is at minimum potential. It kind of swings back and forth. But we still see that difference in like that maximum potential is not equal to that maximum kinetic because of how we made the because of that sine theta equals theta approximation. Yeah. Oh, like saying, sorry, what was it? Yeah. Oh, yeah, it is the same. It's the same equation for both of them. I'm just using the two different. Here, I'll zoom, come back up, so we can see that. Yeah, in both cases, I'm just saying like, all right, linear is whatever linear theta I got, and linear theta dot. Okay. Yeah. So that's this is whenever whenever we're doing like integration by hand, we usually set up like some e to the something t and then solve for it with like the coefficient changing with the computer. It can only integrate for small time steps, and it's always first order differential equations. So it's always got to be like a dx dt equals something x, something, some function x. So in this case, I have angle and angular velocity as my inputs, and the outputs are going to be angular velocity, which is derivative of angle, and angular acceleration, which is derivative of theta. And that's where I can plug in negative g over sine theta. Yeah, now I'm like, it is kind of weird to think about why do we need to do that at the beginning? But there's lots of numerical methods that solve that problem, and none that will solve the second method. That just split it up into two methods. But at face value, like for now, we can take the face value. Okay, it's integrating it, it seems to work. Yeah, you don't have to like regular functions to integrate. At least not in this class. Cool. Seems like we made some progress, had some nice exploring, talked about different solutions, linear and nonlinear, and what's going on there. So let me know if you need anything else, but I think we are done for the week, head into the weekend. Cool, thanks.